which is like the simplest thing of forking or execution that our operating system gives us. And there's multiprocessing. And the difference between those is that threads share memory with each other, whereas multiprocessing is different processes for running. And threads are much lighter than processes. And well, I wanted to show an example in which concurrent execution actually helps us, because there's a lot of different tasks that we actually don't need this. So I don't know if you heard about Montecarlo algorithms, but this is a way of calculating the pi number by generating a lot of random data. So you basically get the hypotenuse, I don't know how to say it in English, about two numbers, and you decide if the number is inside the area or outside the area, and based on that, you have this formula that gives you the pi number. So this is a really simple implementation. It's done in a kind of functional way. And well, if you see in MATLAB, we have random number generation, and we have reduced Z. So this function, what it does is that it counts the number of points that are inside the circle and the number that are outside. And based on that, we get the pi number. So I'm going to show you that. And now, the thing about Monte Carlo algorithms is that the more data that you get, the more exact or approximate the result's going to be. So I'm generating like 10 million numbers there. It's going to take a while. Maybe, I don't know, 30 seconds or something. Maybe more. This is the plan showing. And well, one thing about this is that, as you can see here, there's only one core that's actually executing my Python program, or even as I have 4 cores in this machine. And it's gonna take a while, maybe seconds, no, minutes. And we do it with many cores, it's gonna be faster. Don't worry, we're not gonna be staying waiting for all night. So, yeah, mention. Oh yeah, this is htop. There's a nicer top command. And yeah, there we go. So this is an end that I accidentally typed. 3.1416. And that's with the Py program I was showing. Oh, a little bit too much coding, so you can see. So that's one way to do it. Another way would be, well, where's my threads? And when we are using threads, we are actually gonna be using more cores in our process. And you see there's more Python processes around, Python thread. Well, they're not processes, they're threads. And it's using more cores, but there's a catch, and is that Python actually doesn't do well with threads because it has this thing called the GIL that prevents us from doing multiple operations, CPU operations, at the same time. So even if I'm using more threads, I'm not getting that much speed. But what we did is actually pretty similar to what we did before. The only difference is that I split my random generation in chunks and give every chunk into a thread. And after that, well, I just get the results from each thread and, well, get the results. And if this is using the Q and threading libraries from Python, Q is within Python to, well, what's called the same, but it's not. It's an underscore instead of uppercase. Let's see if it's finished. No, it's still there. So I was saying it's written in a pretty functional way, and well, there are some functions that you're not seeing there because they're the same that there was in the last. And it's still running, still running, still running. And well, yeah, you never get the 100% usage of those cores. But yeah, there we got the result. And threading in Python, well, as I was saying, you cannot use it for this kind of operations because the operation is CPU bound, but there are other operations, for example, making URL requests that you can actually get this to work, and it's actually a better solution than using multiprocessing. But now let's see multiprocessing. And if you notice, it's actually almost the same code. I just, instead of calling threading, I call multiprocessing, and instead of using the Q, I use multiprocessing Q. And this code will use all of my cores. Well, I just this constant there. And let's see how it goes. And yeah, as you see, we're using the full CPU for everything. My machine. There's 4 processes running, and it should go faster. A little faster. It still takes a while. We should have timed this. What? Yeah, or well, I do normally just time command. Yeah. But it is faster and is using all of my cores. And well, there we go. I'm gonna get almost the same result. It's not gonna be the same because, well, it's approximate using Montecarlo and random operations, but it's a pretty good approximation of the high number. But thought this is how we would do it with concurrent futures. Futures, it's actually the same. We're using the thread, we're using multiprocessing, but the thing is that it offers a simpler API and a more elegant or electronic API, let's say. And the thing is that it's really easy to convert what was once not concurrent code to code that actually is. So with futures, we got this process called executor, and it lets you instance an executor with statement. And after that, you just send functions, health functions in each one of the cells. It's so much less. We don't have to deal with the queue. We don't have to deal with anything.
What's behind license? Is it multi-threading? It's multi-processing. Or is it something else? What's behind concurrent license?
It's actually
the reason why I'm asking because there are several other products, right, that try to be concurrent, right? JVM was already, and they work with different.
No, this is simple.
Multi-processing.
Is this modeling a threading behavior?
Yeah, this is modeling a thread processing behavior. But it means that you have this first full executor and our private full executor, and you get just call it.
This is sort of what I'm saying. So going through the new process, through the
Oh yeah, features are one. In this, there's another option.
The features is easy because if you put 7 use the type of values for C-CCP. When you start something, then you fall to the get this out.
Well, yeah, this you can also use the features library for that simple features, and this is the easiest way I use it. Also, I like this hand code because it's kind of functional. And yeah, but you can do features and generate a
whole, like join of the features and then all together.
So this is, and this will actually be the same as the multiprocessing before, but instead of all of that, we just have this. Yeah. Oh yeah, the generate random is still the same. Yeah. No, nothing. Oh well, yeah. You know that you mentioned it. Yeah. Instead of putting stuff in a queue, I do just a simple return statement. So any function that you get, you can use with features, and yeah, there no, you don't have to yield anything.
And it's a part of Python 3, right?
That's part of Python 3, and there's a backport for Python 2.7, so you can install that with pip, and it will work. Good catch idea. Well, yeah, this is the same I was showing you. Well, that's the time. It's gonna start, and there we go. We have it's implied. It does something with the with statement, and yeah, it does it in the with statement by itself. And no, I mean it generates. I mean, let's see. When you do executor.map, you get a generator, and as you consume from the generator, you get the results from each one of the concurrent operations. This one, I just sent the same function. And it took like 2 minutes. Whereas with, well, you remember what we did in the first time? It was like 5 minutes, maybe more, longer. But what I was saying, the really cool thing about this is that with concurrent.futures, well, this is another example. I have this simple script. This is totally sequential code. I have this request URL. So request URL means request to URL and returns and something like returns get the title of the URL from our website. You see there's a map, and to make it concurrent, I just need to change that. The futures, and instead of map, it will map with even the executor. Okay. That's what we need. Code the sequentially, which is sometimes easier to understand. And if you're having any concurrency or more power or whatever you use in check, you're good to go. Most. Yeah. What? Well, to the few things, just like an abstraction of it, describing the multiprocessing API. For me, it makes me simple. So, I wanted to show you this. This is a long scrapper, but yeah, this is the this is scrapes my blog right now actually. See? Sequential. And should be trying. There it goes, one by one. Printing stuff. Let's see how much it took me. Took like 6 seconds. So running it with concurrent.futures. One second.
So in spite of the name of thread, so it's actually a multiprocessing, not thread.
Can you repeat the question?
In the name you have thread or executor, but it's not thread, it's multiprocessing.
No, in this case it's thread. So you have two kinds of
Okay, then implement
process. In this case, as it was an idle operation request from my neurons. Yeah, this.
So since you work with this, what's the benefit of using a thread instead of a process?
Well,
it seems it's hard to
because
go
thread isn't parallel, in fact.
What?
Thread isn't parallel. If it doesn't have commands in parallel, there is a problem with it called G in Python, and it cannot execute several commands at once. It's still running just one thread. On the processor, where multiprocessing does four processes. Or whatever processes we need in the same code.
so with threads, you do have multiple execution, but if you are doing several tasks, that they want to work better. But in this case, because we are bound, I mean the thing that actually stops or slows down the process is waiting for the network or the connection. We don't need CPU, so we do speed up the operation by using threads. So if you don't need CPU bound tasks, you should be using threads because they are like that's it.
Did you do any comparison to G-Link, for example? To parallel and concurrent?
GFNs. This was actually getting all the URLs from the website. Yeah.
Two questions. Does the training API, does it include semaphores?
Sarah?
Semaphores, yes.
Oh yeah.
And the second one is, does this work the same way for Windows, or does it really work with Microsoft or Windows 5, 6, 7?
Sorry.
Does it work on Windows?
Oh yeah, it should work. It's completely standard level question.
It provides semaphores and blocks.
Well, in this kind of operation, it's very functional and we're going to stay in different place. You really don't have to make the example. Yeah, you do have, of course, but
features what I'm asking about JMN because in theory, it has exactly the same exactly between girls and power. Yeah. So not really sure.
I was also going to ask similar, because Pattern 4 has async IO, which I have not looked at, so I'm not very good about it. Have you looked into it?
Yeah, async IOs different. Async IOs I don't know if you guys used it.
Okay. I use Twisted.
So yeah, async IOs is like the same as Twisted, but well, maybe because performance variables and stuff. But what it does is switch this model to a different. It's called I don't know, it's an actual model. But what you do is that instead of working different process, you send request, then you look for an event that the operating system gives you, which you respond to this event like a call, for example. Um, yeah.
So it's more for giving like callbacks rather than doing.
Well, it's not. Yeah, you do have some concurrency, but it's in a different kind of concurrence.
It's concurrent, but it's not one for.
Yeah.
With all process to express the process with all available force is GM or this to just one for, but it's switching functions between different. It's just this way. Like you know, in your closure functions of the center, twisted for GM, you have to yell or something to let others run. In this case, it just switches that call. And if it's waiting on I, you can say, no, you run more days.
Okay.
So those are not for not severe but anywhere else. And yeah, that was my short presentation. There's some links if you want. Probably share this. I don't know if you guys have any other questions.
Are you visiting it or you
No, I'm just in Boots. I work for Rain and they brought us over for a couple of weeks. We worked on part. Yeah, that's good. I haven't gone out that much. Yeah, I know.
You're famous for nice outdoors.
Oh yeah, I want to go to the mountain. Fun. Thank you guys.